Welcome. This electronics tutorial explores the steady-state frequency domain response of an RC low-pass filter circuit. The analysis is done in the QUCS simulator. This is a companion tutorial to the QUCS Getting Started simulation tutorial, which creates the RC low-pass filter simulation. We're looking at AC circuit behavior driven by a sinusoidal voltage source input. The voltage source will be swept over frequency. The impedance of an ideal capacitor is inversely proportional to frequency. As frequency goes up, the impedance of the capacitor goes down.
Let's briefly clarify some detail. Reactance X is one part of impedance Z. Considering capacitive reactance as just the X term in the impedance, and not including the J into the definition of reactance, gives us negative capacitive reactance. The impedance of an ideal capacitor also has a negative sign. Putting the J term into the denominator of the impedance Z sub C might make the impedance look like it is positive valued.
The alternating current input voltage, Vin, applied to the circuit splits across the resistor and capacitor in proportion to their impedances. The lower the capacitive impedance Z sub C, the lower the percentage of Vin that appears across the capacitor as V out. At low frequencies, less current flowing through the entire loop means less voltage dropped across the resistor and therefore more voltage dropped across the capacitor. We don't have to say which current because the current is the same for the whole loop. At low enough frequencies, there is little or no current and essentially all of the input voltage Vin appears at the output as V out. The magnitude of the transfer function, expressed in dB, is used to make the Bode plot. The bars over the top of the voltages indicate phasors in the frequency domain. Phasors have the time component removed. The break frequency, or corner frequency in radians, is 1 over RC for this low-pass filter. To calculate the minus 3 dB frequency, we plug in 2 pi times frequency equals 1 over RC and then solve for frequency f. To verify that omega sub c equals 1 over RC, we can plug it into the equation of the magnitude of the filter transfer function h of j omega. The resulting 0.707, when expressed in decibels, is just about minus 3 dB. Here is the phase response, theta of j omega, of the RC low-pass filter topology, the angle of the transfer function. As frequency increases towards infinity, the phase of the output capacitor voltage approaches minus 90 degrees. To calculate the phase response of the RC low-pass filter, we start with complex numbers, where the angle of a quotient equals the angle of the numerator minus the angle of the denominator. The complex part x of this numerator is 0. Our phase response, theta of j omega, equals minus the arctangent of the quantity omega RC. This is the end of our video. We hope it has been useful to you.